Assalamualaikum. This is your Thermodynamics 2 class. So today is lecture number 15. So can anyone confirm what's appearing on my screen right now?
If you're seeing the introduction slide, lecture 15.
Okay, thank you so much. Okay, so again it is from gas power cycle, which is also chapter number 9. So in the previous class we already talked about dual cycle. Okay, I hope there will be some understanding about the dual cycle, that we have already solved some problems. So in the first part we will solve another problem related to dual cycle, and then we'll start the new topic for the next topic. Okay, so starting from the problem, so first you have to read the statement. So an IC engine operating on a dual cycle, limited pressure cycle. So I already told you that if it is mentioned in the question, either it is a dual cycle or limited pressure cycle, it's mean the same thing. Okay, because dual cycle name is limited pressure cycle. The temperature of the working fluid air at the beginning of the combustion process is 27 degrees Celsius. The ratio of the maximum and minimum pressure of the cycle is 70 and compression ratio is 15. Then there will be condition that amount of heat added at constant volume and at constant pressure are equal. So the process that is taken between 2 to 3 and 3 to 4 and the heat addition process is equal. Compute the air standard thermal efficiency of the cycle. So you have to note on this data, then we will move towards the solution. Okay, starting from the PV diagram first. Okay, so we will draw PV diagram in order to look where the state points are. Okay, so we already know that 1 to 2 there will be a compression process. Then this is your constant volume heat addition. Then it is the constant pressure heat addition. Then there will be a expansion process take place and until 4, and then 4 to 1 there will be a constant volume heat addition process. Okay, so I hope there will be no confusion that how these diagrams will be drawn. Okay, so in your question it is mentioned that the ratio of maximum pressure and minimum pressure of the cycle is 70. Okay, so the maximum pressure takes place at point number 4 and 3, or minimum is at point number 1. Okay, so it's mean that the ratio, which is P3 over P1 is equal to 70. Okay, so this is given in your question. Then it is mentioned that the compression ratio, which is R, is equal to V1 over V2, maximum volume over minimum value volume, is equal to 15. Okay, and then the given thing is temperature. Okay, so T1 is equal to 27 degrees Celsius, or you can convert it into the Kelvin, equal to 300 Kelvin. Okay, so we have to find the thermal efficiency for this cycle. Okay, so in order to achieve this, we can use two methods. First is you have to just find out the pressure ratio, cutoff ratio, and compression ratio is also there, and you can directly put these values into the efficiency equation, which we already derived in the previous lecture. And second method is you have to just find out all the temperatures at all the states, and then you can plug the value into the thermal efficiency equation, which is the function of compression. Okay, so we will try to find out that how to find the temperatures at different points, so that we can plug all the temperature values into the efficiency equation. So coming towards the temperature value for T2, because T1 is known to us, so T2 is equal to, okay, so T2 we can apply an isentropic relation, which is T2 over T1 is equal to V1 over V2 K minus 1. Okay, so from here we can also say that V1 over V2 is equal to 15, 0.4, 1.4 minus 1, and T2 is equal to 300 into 2.954, which is a solution of 15 exponential 0.4, and then it turns out to be 886.2 Kelvin for the T2. Okay, so T2 is known to us. So now coming towards the T3. So in order to find T3, it is a constant volume heat addition process. So we can apply the relation that is P2, V2 over T2 is equal to T3, V3 over T3. And from here we can easily eliminate the volume because it is a constant volume process, and that equation turns out to be T3 is equal to T2 into P3 over P2. So now the problem is that we do not have the value of P3, and also we do not have a value of P2. Okay, so P3 value we can easily find from this relation, which is P3 over P1. So we can say that P3 is equal to 70 P1. Okay, and for P2 value, okay, so now the issue is with the P2. So for P2 value, we can also apply one isentropic relation between 1 to 2. So we can say that P2 over P1 is equal to V1 over V2. Okay, so this relation is also valid for the isentropic processes. Okay, so from here we can say that P2 is equal to, okay, V1 over V2 is equal to compression ratio 15 to power 1.4, and if we can solve, it turns out to be 44.3 into P1. So now P2 is also in terms of P1 and P3 is also in terms of P1. So we can easily put the value because 886 is given from the previous step, and P3 value is 70 into P1 and P2 value is 44.3 P1. Okay, so from here we can eliminate the P1, and if we can solve, we can get the value of P3. Okay, so P3 value we can find as 1400 Kelvin by just solving this equation. So T3 is also known to us now. So now we will find the value of T4 and T5. We can note it down, then move towards the next one. If you have any question, you can ask me. Okay, so from the question, it is mentioned that the amount of heat added at constant volume and at constant pressure are equal. So it means that this Q and this Q is equal. Okay, so from here we can say that Q 23 is equal to Q 34. Okay, and by using this thing that which is the condition that is given, we can easily find the value of T4. Okay, so if we can say that Q23 is equal to CV T3 minus T2, and which is equal to Q34, which is constant pressure process, so Cp T4 minus T3. Okay, and if we can just solve it for T4, so it turns out to be T4 is equal to T3 minus T2 over K, because Cp or Cv is equal to K. Okay, so now we have the value of T3 with us, T2 is also known to us, and K value we can easily find from the thermodynamic table A2, which is 1.4 for the air. Okay, so we can just plug the value, and it turns out to be 1400. T3 value 1400 minus K, that is 6.2, and then the value of K is 1.4. And from this we can solve it, and it turns out to be 1767 Kelvin. So now T4 is also known to us. Okay, so now this last point is T5. So T5 we can easily apply one isentropic relation between 5 to 4. So it turns out to be T5 over T4 is equal to V5 over V4 and its power is K minus 1. Okay, so now we do not have the value of V4 with us and V5 is equal to V1, okay, from the PV diagram, and we have to find first the value of V4. Okay, so in order to find the value of V4, we can apply one relation between point number 4 and 3, which is P3, V3 over P3 is equal to V4, V4 over V4. And it's a constant pressure process, so we can easily eliminate pressure over there, and then it turns out to be V4 over V3 is equal to T4 over T3, and T4 value is with us at 1767, which we already find in this step, and then T3 value is also known to us, that is 1400. Okay, so now if we can just solve it, V4 over V3 becomes 1.26. Okay, so now from the compression ratio which is given in the question, R is equal to V1 over V3 and R value is known to us. So from here we can say that V3 is equal to V1 over 15. Okay, so this is from the data which is available in your question. Okay, so if we put the value of V3 in this equation, which we already said V4 over V3 is equal to 1.26, it turns out to be V4 is equal to 0.0 84 into V1. Okay, so if I just put the value of V3, which is this one, V1 over 15 into the equation, you can say it is A equation. Okay, so now V4 value is also in terms of V1. Okay, and V5 is equal to V1, so we can easily eliminate the value of V1. If we can put in the value, V5 is equal to V1 and 0.084 V1 and then 1.4 minus 1. Okay, so V1 can be eliminated over there. And T4 value is already with us, that it is 1767. And it turns out to be 2.6. And the T5 value becomes 656.9 Kelvin. Okay, so now all the values of the temperature are with us, so we can easily find the value of the thermal efficiency of the dual cycle. So you have to note it down, that we move to the next one. If you have any questions, you can also ask. So for the thermal efficiency, we already know that it is equal to 1 minus Q out over Q in, and Q out for the dual cycle is CV T5 minus T1, and Q in is equal to the combination of constant volume heat process T3 minus T2 and plus constant pressure heat process, which is between 3 and 4. Okay, so from here we can easily say that it will be equal to 1 minus T5 minus T1, T3 minus T2, and if I just take a common of CV from both of the sides, so it becomes K value and T4 minus T3. This equation we already derived in the previous lectures. Okay, so now we have all the values because T5 is known to us, T1, T3, T2, T4, T5, and K value is also known to us. So if I just put the value T5 656.9, T1 300 Kelvin from your problem statement, T3 is 1400 Kelvin, T2 value is 886.2, plus K value is 1.4, T4 value is 1767, and then T3 value is 1400. And you can just solve it with 0.653 or it is equal to 65.3% of your dual cycle efficiency. Okay, so this is the solution for this type of question. If there will be mentioned that the pressure or the maximum pressure and the minimum pressure ratio is given, and if you do not have the value of cutoff ratio, or also you do not have the value of pressure ratio, which is the beta, so then you have to follow this type of procedure. Okay, so if you have any question, you can ask me, and then we'll move towards the next topic. Okay, so now there are two assignments. Okay, so which you have to submit it to me by next 10 days. Okay, so this is a very easy assignment. I think it will just take hardly 1 hour to complete it. So first is to state 4 reasons why the actual thermal efficiency is different from theoretical value in gas power cycle, that is Otto, diesel and dual cycle. Okay, so you just have to state 4 different reasons. Okay, so I hope you have all the clear idea and why your actual thermal efficiency deviate from the theoretical value, because whenever we have to assume that there will be a theoretical value, there will be some assumptions, okay? And mostly we can just say that there will be ideal cases we are assuming, and then definitely it turns out to be the deviation in the thermal efficiency. So you have to just think about it. What are these reasons? And then assignment number 3, you have to just put this graph. So from this graph, you can notice that the Otto cycle efficiency is maximum as comparison to dual cycle efficiency as comparison to diesel cycle, or you can say that the dual cycle efficiency is in between Otto and diesel cycle efficiency. Okay, so the assignment is that you have to prove that your dual cycle efficiency which is here, is in between the diesel and Otto cycle efficiency, and you have to just draw a TS and PV diagram only, okay, for this. Okay, so do not have to go for any calculations or any mathematical procedure, and you have to just assume that for the same compression ratio and the heat supplied is the same for all the cases. So what you have to do is you just have to draw one TS diagram and one PV diagram. Okay, so this is TS, this is PV diagram, and you have to draw all 3 cycles. Okay, so all 3 cycle on the one TS diagram and all 3 cycle on the one PV diagram, and you have to just compare the area under the curve, and then you can just correlate it with it that which cycle is more efficient and which cycle is less efficient by just visually inspect that which area under the curve is minimum and which heat rejection is minimum. So then you can easily judge the values that your dual cycle efficiency is in between Otto and diesel cycle. So if you have any question, you can also ask me related to assignments. Okay, and you will take next 10 days, and you can submit it to me after this 10 days.
Sir, submission will be on MS Teams or LMS?
It is on MS Teams.
Okay, thank you, sir.
MS Teams, you just have to take a snapshot of your work and just send it to me, and then I will mark the assignments. Okay, so if you have no question regarding to assignments, then we'll move towards the next topic. So for the next topic, we have other cycles that's named as Stirling and Ericsson cycle. Okay, so these cycles are also a gas power cycle. Okay, so but the main difference in the Stirling and Ericsson cycle from the Otto, diesel, and which dual cycle is that dual cycle and dual cycle Otto and diesel cycle is internal combustion engines, that the combustion take place inside your cylinder. However, the Stirling and Ericsson cycle, these are the external combustion engine, that your combustion take place outside of your cylinder. Okay, so this is the main difference between the Stirling and Ericsson cycle. Now coming towards that ideal Otto diesel cycle are not totally reversible. However, since they involve heat transfer through a finite temperature difference during the non-isothermal heat addition or heat rejection processes, which are irreversible. So it means that in the Otto, diesel and dual cycle, there are irreversibilities involved in it. So that's why the efficiency of the Otto, diesel and dual cycles are less as comparison to Stirling and Ericsson cycle, because in Stirling and Ericsson cycle, they involve isothermal heat addition and isothermal heat rejection process. So that makes this cycle more efficient. So therefore, the thermal efficiency of Otto and diesel cycle will be less than that of Carnot engine operating between the same temperature limits. An important point is that the efficiency of Stirling and Ericsson cycle is almost equal to Carnot cycle when we are operating between the same ranges of the temperature. Okay, and then there are two other cycles. So here we already talked about that there will be isothermal heat addition process and isothermal heat rejection process, and that is the Stirling engine and the Ericsson cycle. Okay, so we will see that what is the difference between Stirling cycle and Ericsson cycle in the coming slides. So they differ from the Carnot cycle is that the two isentropic processes are replaced by two constant volume heat regeneration processes in the Stirling cycle and two constant pressure regeneration process in the Ericsson cycle. Okay, so if you can just correlate with the Carnot cycle TS diagram, you can easily find that there will be two isentropic processes are also involved in the Carnot cycle. However, in the Ericsson and Stirling cycle, there are no isentropic processes are involved. Instead, there are two processes which are the constant volume regeneration process in the Stirling cycle, and there are two constant pressure regeneration processes in the Ericsson cycle. So this is the main difference between Stirling and Ericsson cycle. Okay, so now we will discuss about what are the cycles are involved in it. Okay, so we can start it after break because it's take time, and if we can just stop in between. Okay, so we will take, I think, break for the prayer, and then after prayer breaks at 1:30, we will again meet, and then we will discuss about the cycle and how different processes are involved in the Stirling and Ericsson cycle. If you have any question, you can ask me, and then we'll move towards the break. So starting again from the Stirling and Ericsson cycle. Okay, so now we will look for the processes that are involved in the Stirling and Ericsson type of engines. Okay, so here the schematic shown over there. Okay, so the process 1 to 2 is your expansion stroke, and as you see in this schematic that there will be two pistons in your Stirling cycle. This is one piston and this is your second piston, and then there will be two cylinder also. Okay, so we can say that this is your cylinder number 1. So you can say it is cylinder 1 and you can say it is cylinder number 2, and this cylinder is the at highest temperature at TH, and this cylinder is at the cooler temperature or T low. Okay, so as I already told you that Stirling engine or Ericsson engines are mostly are the type of external combustion engines. Okay, so here what we have to do is we have to supply heat to the water cylinder, which is cylinder number 1. Okay, that can be either by mean of burning coal, either by burning fuel, or either through solar energy. So we have to use various type of fuel in order to provide heat to this cylinder number 1. Okay, so once we added the heat to cylinder number 1, so it's mean that whatever the working fluid inside it, so most commonly we use helium or hydrogen gases for the Stirling cycle. However, air is also used for it. Okay, so the working fluid that is in the cylinder number 1 is already now at the hottest temperature because it is heated also, and then for example at your state number stroke number 1 to 2, your piston is at your, you can say it is at your top dead center where there will be minimum volume. So it start moving down, and for your when there will be a heating process, and then the expansion take place over there. Okay, so it's mean that your cylinder, your piston will move towards your bottom dead center when there will be a expansion process. Okay, so there is another component that is added in the Stirling cycle, which is the regenerator. Okay, so this regenerator is basically designed by using the high thermal mass material. Okay, so what is the purpose of this regenerator? So this regenerator basically serves as a temporary storage mean of your energy. So it's mean that we have to just store energy from this working fluid, which is at the highest temperature, and then we send it to the regenerator. So this regenerator store that energy, and then it releases towards this cylinder number 2. Okay, and that cylinder number 2 is at the lower temperature. Okay, so the only purpose is to temporarily store the energy and then release back and forth towards the cylinder 2 and cylinder number 1. Okay, so we will look for the process also, and we will talk about other processes. Okay, so this is your stroke number 1. Okay, so expansion takes place at your cylinder number 1, and then after this there will be 2 to 3 process. So in the 2 to 3 process there will be a regeneration process. So this is basically regeneration is typically word used when there is a transfer of energy from cylinder number 1 to cylinder number 2. Okay, so now regeneration takes place, and what we have to do is, for example, this piston is at this time at the bottom dead center at the maximum volume, so it start moving towards the top dead center. So now it is just started. Okay, so it's mean that whatever the working fluid is occupied in the cylinder number 1 will now move towards the regenerator side, and whatever the energy it is, in this working fluid, which is at TH at this time, stored over there, and then it will be sent back towards the cylinder number 2. Okay, so the cylinder number 2 at this time, so cylinder number 2 is at this time at TC, so it's mean that it is for the first for the process 1 to 2, this is at your top dead center, okay, at the minimum volume. So it just start moving back towards the BDC for the process 2 to 3, and this is I am talking about the regeneration process. Regeneration takes place. So it's mean that now the expansion take place over there. Okay, so in this cylinder, okay, because the working fluid is shifting towards here in the cylinder number 2, and the expansion take place. So this piston move towards the BDC. So now the process 3 to 4. So in the 3 to 4, the piston is already at the BDC, and now it start compressing the working fluid which is inside your cylinder number 2. And once there will be a compression process take place, so it's mean that the working fluids, the temperature of the working fluid increases because compression increases the temperature. So it means that there will be a rejection of heat for the compression process. So another important thing is that when you have to correlate with your Otto cycle and diesel cycle, you see that the combustion process take place separately and expansion process take place separately. However, in this case of Stirling cycle, expansion and your Q addition process take simultaneously, and also your compression process and heat rejection process take simultaneously at the same stages, which is at 3 to 4 and 1 to 2. Then there will be a constant volume heat regeneration process also. Okay, so in this process, so whatever the temperature of your working fluid is at your cylinder number 2, now the working fluid move back towards the cylinder number 1, and this regenerator store the energy and then it releases back towards the cylinder number 1. Okay, so in this case, your piston now again move, which is at your TDC, comes again towards the BDC. So this is the processes involved in your Stirling cycle. Okay, so now we will see one video also so that you will get a better understanding how different processes take place for your Stirling cycle. Okay, so now you have to see one video, then we will discuss further about it. Okay, another important point is that Stirling's engine has many types. So there are alpha, beta, gamma, depending upon the piston cylinder arrangement, but the working principle is almost same. Okay, so now we are looking towards the alpha type of Stirling engine. Okay, so here, which I have already explained, that there will be a combustion process. So it's take place externally. So we are heating this cylinder by using the external source of heat. And once it is heated, it is at the highest temperature, which is your T highest point, and you can say it is a hotter cylinder. And the expansion takes place inside it, and then there will be a cooler cylinder also. And this is the way through which we can send the working fluid back and forth towards the hotter and then towards the colder cylinder. And this wire mesh, which is shown over there, is basically your regenerator, which is developed by using the high thermal mass, any material which is a high thermal mass. Okay, so these are the components, and now we will just move further. Okay, so here there is a ball showing over there, so which means that the working fluid go from colder to your hotter cylinder, and also from hotter to colder, and then there are also 4 strokes involved in it. Okay, so I hope you will get some idea about it, that what is the working principle of Stirling cycle. So if you have any question, you can ask me, and then we'll move towards the TS and PV diagram of Stirling cycle and Ericsson cycle. Okay, and the main difference between the Stirling and Ericsson cycle is only for these two processes. So in the Ericsson cycle, this takes place at the constant pressure regeneration process, and for 4 to 1 it is constant pressure regeneration process also, and rest of these processes are same. Okay, and also schematic diagram is almost same for the Ericsson cycle. Okay, so these are some points which we already discussed about it, that unlike internal combustion engine, a Stirling cycle does not exchange the working gas in each cycle, and the gas is permanent, and the heat is supplied outside the engine, so any heat source can be used. So that will be a good thing, that we can use coal, gas, solar energy, nuclear power, or many type of energy we can use, because combustion takes place outside of your cylinder. Then Stirling engine can reach high thermal efficiency than the Otto and diesel engine, since heat transfer occur at the constant temperature, and that is its thermal efficiency is same as that of Carnot cycle. Okay, because there are no irreversibilities in your Stirling engine and your Ericsson engine as well. The pressure changes are very smooth and its torque is uniform. It has no valves, exhaust pipe, etc. The Stirling cycle is quiet and has less maintenance work. Okay, so these are some positive things about it, but still, Stirling and Ericsson cycle are not practically used in our daily life. For example, for the automobiles and for power generation processes. However, we can use these type of engine just for the practical purpose and for the understanding point of view, that how Stirling and Ericsson cycle works and what are the basic principle. But still, there are a lot of research that are doing on the Ericsson and Stirling cycle, so that we can make, because the main important point is that there are some flaws in the Stirling and Ericsson cycle as well. So we will discuss about it in the later slide, why we are not going to build these type of Stirling and Ericsson cycle. Okay, so coming towards the TS and PV diagram, so we already discussed that there will be expansion process, constant volume degeneration process, isothermal compression process, and then constant volume degeneration process. And these are the four processes that are involved in the Stirling cycle. Okay, so first we will draw the TS diagram. Okay, so coming towards the point number 1 to 2. So as it is an isothermal process, it's mean, for example, this is your point number 1, and you can just draw a straight line, and this is your point number 2, and the temperature is constant from 1 to 2. And then there is a constant regeneration process and the internal energy, the internal heat transfer from the working fluid to the regenerator. Okay, and I have already told you that the basic difference between the Carnot cycle and your Stirling cycle is that there will be involvement of non-isentropic process. So the 2 to 3 process is not isentropic. Okay, so it means that your entropy will decrease because this is the regeneration process. So for example, this point is over here. So then 3 to 4, it is again a heat rejection process, and it is isothermal. So it means that the heat rejection and take place isothermally. And then your 4 to 1, again it is a regeneration process and internal heat transfer from the regenerator back to the working fluid. Okay, so it means that your entropy slightly decreases. Okay, so here the cycle is, okay, if you compare with the Carnot cycle, you can see that there are a lot of same things, because 1 to 2 process is same, 4 to 3 process is same. Then you can say V is equal to constant and V is equal to constant, and this is your Qin, and during the expansion process the heat is supplied, and during the compression process heat is also rejected. So these processes are shown. Okay, so then there will be a regeneration process. So in the regeneration process, what we are doing is we are transfer energy from process 2 to 3 to 4 to 1. Okay, so it's mean that we can show the regeneration process by using the zigzag arrow, and we can say the regeneration take place from 2 to 3 towards 4 to 1. Okay, so this is the TS diagram, and then we will move towards the PV diagram. Okay, So coming towards the process 1 to 2, so as it is expansion process, so it's mean that the volume, whatever the volume is at point number 1, so for example, this is your point number 1, so volume at point number 2 increase, okay, because this is the expansion process. Then your 2 to 3 process is the constant volume regeneration process, so it's mean that until point number 3, the volume is constant. Then 3 to 4 is your compression process. It means that the volume at point number 3, when it's moved towards the point number 4, is decreased. Okay, so it means that this point will be somewhere there. So the volume is shifted towards the left side. Okay, so now coming towards the process number 4 to 1, which is a constant volume process. So it means that volume at point number 4 and point number 1 is equal. Okay, so this is Q in, this is your Q out, and this is volume constant, this is volume constant. And now the regeneration process, let's take from 2 to 3 towards 4 to 1. Okay, so it means that we have to just draw one arrow and we can just shift towards the 4 to 1. Okay, so this is a TS and PV diagram for the Stirling cycle. Okay, so if you have any question you can ask, and then we'll see the Ericsson cycle also of TS diagram. Okay, so coming towards the TS and PV diagram of Ericsson cycle. Okay, so if you can just compare with the Stirling cycle, you can notice that the process 2 to 3 and your process 4 to 1 is only different, okay, as comparison to the Stirling cycle. Constant pressure regeneration process and constant pressure regeneration process between 4 to 1. Okay, so now coming towards the TS diagram first. Okay, so for 1 to 2, it's take isothermally, so it's mean that your temperature 1 to 2 is constant. So then there will be from 2 to 3, it is a regeneration process and take place at constant pressure. Okay, so you can just draw one line over there, okay, because the entropy will slightly decrease over there. This is a non-isotropic process. Okay, you can just mark that pressure is equal to constant. It's now 3 to 4, again it is a isothermal compression process, so it's mean that until process number 4 temperature is constant, and then 4 to 1. You can just mark P is equal to constant. And this is Q, rejected, and then the regeneration takes place from 2 to 3 to. Okay, and you can just notice that the TS diagram is almost same as comparison to the Stirling cycle. Okay, so only there is two processes which are different, which is at constant pressure. Now coming towards the PV diagram. Okay, so again from 1 to 2 expansion process, so it's mean that your volume, for example, at this point is here, and then at the end of your expansion process, it will be there. There will be increase in volume, and then from 2 to 3 is the constant pressure regeneration process. So it's mean that pressure will be constant, and this is your point number 3. Then 3 to 4 is the compression process. So it's mean that your volume decreases. Okay, so you can say that your point number 4 will be somewhere there. So you can shift it towards the decrease in volume, and then 4 to 1 it is the constant pressure regeneration process. So it's mean that the pressure is constant. Here there will be Q in, and this is your Q out, and this is P equal to constant. This is P equal to constant. Okay, now in order to smart the regeneration process, so from 2 to 3 to 4 to 1. Okay, so we can say here is the regeneration taking place from and energy is transferred from 2 to 3 to 4 to 1. So this is the PV diagram for the Ericsson cycle. Okay, so if you have any question, you can ask me, and then we'll move towards the next one. Okay, so here the clear presentation of the PV and TS diagram so that you will get the better understanding of it. Okay, so if you can compare with the Carnot cycle TS diagram, you can see that the difference is only between these processes. Okay, you compare with the TS diagram, and then if you can compare with the PV diagram, you can easily notice the difference for the cycle PV diagram. Okay, so to achieve the competitive efficiency, it need to work on a high pressure, which cause the tremendous problem of sealing. Okay, so this is the main issue that why we are not going to build these type of Stirling in Ericsson cycle, because there are high pressures involved in it. Okay, so that will be the cause of the sealing problem issue. Okay, and then the isothermal expansion, isothermal compression, constant volume depressurization, and constant volume pressurization. Okay, so we already talked about that why we are not going to build the Carnot cycle, because there are two processes that are involved, are the isothermal heat treation process and isothermal heat rejection process, and we cannot make isothermal processes for the heat addition and isothermal for the heat rejection easy. Okay, and then the temperature difference should maintain high for the acceptable thermal efficiency, and this result in large thermal stresses in the cylinder. Okay, and consequently, high strength expensive material should be used in order to develop such type of cycle or such type of engines. Then the working fluid has to be an ideal gas. So in this case, mostly we use helium or hydrogen for the Stirling cycle because they have the high heat conductivity and low molecular mass, which lead to the faster heat transfer. However, air is also used in the Stirling cycle. And fast changing in power output are not easy to achieve, which make the Stirling cycle not so attractive for the automobile application. And then if we compare the efficiency, then of your Stirling cycle, Ericsson cycle, and Carnot cycle, all three efficiencies are equal to 1 minus TL over TH. And when we are operating between the same thermal ranges, for example, maximum temperature is same and minimum temperature is same. So you can notice that your thermal efficiency is equal to the Carnot cycle efficiency for the Ericsson and the Stirling cycle. Okay, so these are some positive things about it. Okay, so now we have to just we have not enough time so that we can solve one problem. Okay, so if you have any question, you can ask me. And for today lecture, we will just stop over there, and then from tomorrow we will discuss further about it. Some problems related to Stirling and Ericsson cycle.